Okay, so maybe you hadn't noticed it, but up until that last lecture, everything was a change in S. I had never written S itself. So, and then we spent some time talking about what the real equation is for entropy, not the change in entropy. And again, this is normally not taught in this class. It's a graduate level thing. And now I've written this expression. This is how I do a single molecule, and I know that because I wrote KB, Ln number of microstates. For the purposes of this class, I'm just going to define microstates as like how many places can a chess piece sit on a chessboard. That's on your homework. And what I have you do, and again, just to get kind of a feel for, I mean, again, I can't just transport you to grad school and spend about a month setting this up, but what you do on your homework is you're going to figure out an initial state, how many microstates are of this chess piece on the chessboard. Then I pretend that the chess piece has a reaction and doubles itself as babies. So then you can figure out the entropy of the final state. And there you go, there's your delta S. Just like we've been doing delta S is CV, Ln, TF over TI, blah, blah, blah. And then I asked some questions, that's question 10, on relating that back to what you have been learning, as you should be learning. Is this reversible or irreversible? And that may seem out of nowhere, by the way, so you're going to calculate all these delta S's. And then I'm going to say, hey, is this reversible or irreversible? And the way you think about that is just look at the entropies. All right, so that's a hit. I can't really say anything more without giving away the answer. Anyway, now for the extra hour, I'm going to do a bunch of, we're going to just do derivation after derivation. Really the next 3 or 4 lectures are just derivation after derivation. And again, I want to point out that dx, dy, constant z, I have 1,300 of these. I don't think I've ever asked the same thing twice. In fact, I'm often discovering new ways to do derivations that I had never seen before. Not that they're not known, it's just that you're not going to find a textbook with all 1,300 derivations in it, because why would you? Anyway, now, unfortunately what we're doing today, I almost hate to do this to you at this point, but we're going to expand the toolkit of derivational tools. And again, the best way to get used to this is examples, because I want you to approach this as not as a memorization exercise. As I said several times, I've really got to do this for me. Don't try to memorize any particular example. Remember how we did it. And then just be flexible for when there's different letters, because for all intents and purposes, there is an infinite different set of letters that I can use. Okay, anyway, so now I'm going to review back. I'm still reviewing what we did at the end of last time. I was kind of rushing. Now, another thing, this is something you definitely want to be able to do, is, all right, changing U, this is heat and that's work. All right, now we now have this new expression for heat. Everything's reversible because it can be. Now you're used to work, that's heat. And you always have to be able to map this onto our very simple expression for the change of a function. That function is U. So if you get lost on an exam and I start going down this rabbit hole of using this for a question, start doing stuff like this. F is U, X is S, Y is V. Take some time. This would be one of the harder questions. Take some time, write this stuff out, and anyway, then you can answer whatever I'm asking. Okay, so with that said, I can see that this function has natural variables of X and Y. So internal energies, natural variables are S and V. The conjugates of S is T. And again, you see I've matched these up, and you see why I've done this. Don't forget though, the conjugate of V is minus P. Don't forget that minus. And I tried to look at the exam, the last question that basically everyone did. You saw me do some Legendre transforms with something that was negative. Anyway, don't worry about it. All right, then we talked about Legendre transforms. If U has a natural variable of V and I want to get rid of it, I subtract. Be careful. This is how you'll mess this up, and I swear this is going to have to be on the exam whether I want to or not. This is U. It is not the change in U. That is what you will blow up if I ask this question, which I very likely will, something like this. This is U. You subtract the variable you don't want times its conjugate. The conjugate happens to be negative. That's just happenstance. And of course, that's h. Now, you've known that. Hopefully I said it enough that it's down at this point. Now, what I'm doing here is now I want to get rid of the offending variable of s. S is used natural variables. So now I want to get rid of that dependence. And so I subtract out its s times its natural conjugate. I'm just emphasizing that temperature is positive, plus T. It's not literally s plus T. It's just it's times plus T. I just want to emphasize it. Remember I told you at the very beginning, the fact that work is minus PV always throws a little monkey wrench in everything? It's here. This is what I was talking about. T's and S's and P's and B's always have a minus sign in front of each other relative to one another. That's because of that. Okay, and this was H and this is A. And I even talked a little bit, well, I'll just go ahead and do it. I probably should start looking at my notes before I start rambling off. Okay, if I subtract out the entropy dependence and I also subtract out, even though that's a plus, it's technically minus because P is really minus. If I get rid of the volume dependence, then I've got Gibbs energy. Okay, I'll be getting more into that later. Oh God, now what do I want to say? All right. I'm going to start with A, because A is a Legendre, there's only one step to that Legendre transform. G, all the derivational questions with G, they're not hard, they're just like one extra term because there's one extra term. All right, so here's A. Let's start with A and then I'll do G. Now again, I hate to do this, but now that I've got this guy here, and now I've got A, now I've got G, now I can ask a whole bunch of different derivational questions, so expect this for the next 3 lectures or so. And so remember, I had you do du, dp, or something like that. Well, now I can do dg and dA. Question?
How did you go from the above equation, the derivative of u, down to the equation below, where it's not a derivative anymore?
No. What I'm doing here, you got to remember the Legendre transform equation. But now, what I get from this is that u is a function of s and v, just by mapping this. All right. Now, remember the Legendre transform. Let me use some shorthand. Is when you get a function and subtract its natural variable times the conjugate of that natural variable. Right. That's a Legendre transform, and that's what we did here. Now, recall that if you want to prove, so I contend here that h has s as a natural variable because I never Legendre transformed it off, but not v, but p, because I Legendre transformed it off of u. Now, the way you do that, and you guys did not do this on the exam, although we had covered this last time. It was towards the last material, but kind of thought you should have been able to do this. Change in u plus the change in PV. Okay, so again, if I want to prove that h has natural variables of s and p, I do it by the partial. Okay, and again, this is just basic calculus rules, minus TDS minus PDV. Now you need to know the product rule, plus PDV plus DDP. And cancel. And you see I've got TDS, so there's my S, plus DDP. There you go. H is a function of S and P. I'll do A and G in a little bit. Let me roll a little bit with A, and then I'll do that partial, and then let me do where you want me to do it now?
Well, like, why is the V, S? Isn't X in correlation with S?
Well, yeah. I mean, so this is a function. So
wouldn't it be U?
Wait. So this function has x and y as natural variables.
Yes.
Literally, just at a very almost childish level, f is u, x is v, y is s. Okay, that's kind of childish, but sorry, I interrupted.
Yeah. So if you look at dy, it correlates with dv above.
Yeah, sure.
But so shouldn't it be s, v? You have v in the x spot.
Whatever, man. That doesn't matter. Well, sure. Sorry. No, it doesn't. Okay. Yeah. I mean, look, it doesn't. So if I had if I had just randomly started with x, I could have said df dy, df dx, dx. I could have written that. It doesn't matter.
Well, if you switch around your x and y, doesn't it change your Legendre transform? What you use for x then?
Wait, hold on. Okay, so you're really getting way concerned that x is s and y is v. Don't worry about that so much. Yeah, so I kind of messed up here. I should have written it s and v, but it's just not that important.
Well, I'm just trying to follow, because if you go to the transform, you have f minus x.
Oh, sure.
So try to correlate where you got x from.
Okay, so let me do A. So what I've done here is, again, I'm kind of not being consistent with my x's and y's. So that's the problem. Sorry about that.
Because that changes the whole thing, correct?
But no, because you're too hung up. So I'm making a mistake by I'm switching x's and y's, to be honest. But I'm doing it because they're just letters. So it doesn't really matter that much. But I am not being consistent. Sorry about that. Okay, so because I had so let's do this one, and I'll be careful, and x is s, and the other guy is t. Okay, now the other Legendre transform is this. See, I mean, again, these are just letters. They just don't matter. And this is h, right? Because y is v, and the other guy is minus p. Okay, so regardless, let's just go ahead and do this one. Okay, changing u minus the change in ts. Okay, and minus pdv plus tds. If I think about it, minus TDS, minus SDT. Okay, minus PDV, minus SDT. Now remember that's the change in there. Okay, now from this is the proof that A has natural variables of V and T. There you go. So, I'm being inconsistent. I'm sorry about that. I don't want to do anything to make it even slightly harder when you're learning this for the first time. It's easy for me because I've been doing this 15 years. That just blows past me. But at the same time, I'm also a little bit right here because these are letters. I mean, they don't matter what the letters are. Just keep it, once you've decided that X is something in here, so what I screwed up was all of a sudden I made it V. So, but once I did that, then I was consistent. Then it was U minus V times minus P. But you're right, I did switch that. So, we're okay? Right, so, okay, so now let's just continue on here. Now I've got this new function, A. It's Legendre transformed. I've now shown you that it has natural variables of V and T. And so what? Actually, A and G are very special. A and G are very special in the ways that U and H are not. And that's because they capture the effective entropy. So think about, all right, now when I integrate this damn thing, the delta A, I know the board's getting horrible. Let me just write something in think real quick. Let's think of delta A as A final minus A initial. While it will capture the energy that the molecules have, it will also capture changes in their TS. So let's say we're at constant temperature. What A does is it represents what's happening thermodynamically to entropy in a way that internal energy does not. Entropy, hopefully has been drilled into your head, is horrifically important. So that's why A and G they have a special title. They're called free energies. U and H are not free energies. These are free energies. People say that these represent the total energy available to a system, which is very unsatisfying. And I'll explain a little bit about what that means. A and G are way more important than U and H. That's the big picture. But I have to start with U because U is easy, right? U is just the energy a molecule has. And hopefully you could visualize that, right? That's, argon and it's moving around. Now, anybody can understand that, and then there's more than one argon. Okay. I tack on to U, PV and minus TS. I tack those on. That's a little harder. That's why I do those second. especially all this natural variables and Legendre transforms. It takes a while to get there. But now that we're there, hopefully you're seeing how the TS component in the final state minus the TS component in the initial state, this is terribly important because it's giving me information about what is happening entropically. And so, anyway, with that, let me now show you all the new tricks. This now has a bag of tricks that we can do with it. With A, I'll start with A and then I'll end with G. Now, one thing about U, so I am, as much as I just bashed U and H, there were some things that we always could get out of them, which is that when their natural variables were held constant, they turned into other things that are useful. And let me remind you that change in U, and I don't know if there's some big picture to this. I'll write it this way. So if we make volume constant, I have to write that so you don't get confused in your notes. Constant volume, U was heat. And heat's important because machines are powered with heat. So that was nice. If I held V and P both constant, tell you what, let me write that out. Now that you're used to my formulation for heat as TdS minus PdV. Now here's something funny. One of you actually latched onto this, and I kind of dropped it because I didn't really want to talk about it. Constant S and V. The change in U has to be less than or equal to 0 for total entropy. Want to write this consistently. For total entropy to increase. Okay, so again, start holding natural variables constant. This is just a review. Hopefully you've got this down, but if not, here it is again. When natural variables are held constant, these energy terms turn into things that are like really kind of important. Heat is very important, and does it happen or not? Is it spontaneous? Pretty important. Second law. Now, one of you actually blurted out, and I purposely ignored you. One of you said, wait, changing U is 0. It's always just 0. Not less than or equal to 0, just 0. Now, why did that person say that? Now, that person ostensibly is right. Why?
Because if S is constant, then ds is 0, and if V is constant, dV is
0.
And anything multiplied by 0 is 0, and
0.
0 is 0 is 0.
So where's the negative? Anyone have any idea? Maybe you covered this in thermo. So what's happening is, after the next exam, there's actually another set of terms. And I'm just not writing them down yet. Those are terms that represent chemical reactions. Since we're not doing them yet, I've left them off. So those are the energy terms for chemical reactions, or chemical potentials. Right? I haven't shown you chemical potentials yet. So U actually can be negative because chemicals are turning into other chemicals, and if that reaction goes, you get a negative change in U. Anyway, that's a bit of a preview. I shouldn't be mentioning that now because we got other stuff to cover. So it's just one of you did blurt that out last time, and I wanted to cover it a bit. Okay, anyway, and I'm not supposed to be talking about changing U. I'm supposed to be talking about changing A. Okay, at constant, what am I going to hold? Well, let me write this down. Minus SDT minus PD. I always remember that A is the one with everything negative. H is the one with everything positive. Don't memorize that. You'll figure it out. Okay, now what does this do? Let's hold one of its variables constant. At constant T, the change in A is minus PdV. What's minus PdV?
Work.
Yeah, right. What kind of work? Yeah. Reversible work. So it's kind of this symmetry. We have A and H, which are kind of the lesser thermodynamic functions. They can be heat. Not that heat's important, but heat's job is to be turned into work. This is what we do with it. And now I've got a thermodynamic variable that represents that. Oh, so long as one of its natural variables is held constant. This is how we extract information from these things. In fact, I remember I said that, all right, this is Helmholtz energy. A comes from I think the word is Arbeit. German? Who speaks German? There's a couple of German speakers, right? Anyone, I thought, what does it mean? What was it?
I don't know that word.
That word, it's work.
What
Right,
is it?
A is the German word for work. That's where it comes from. So now, if you ever feel stressed out, I always tell people just close, if all this letter stuff, close your eyes, and count from 1 to 10, screaming in German. Right, that'll calm you down. So that's where we get the letter A. Now, what I want to do is go back to this. Now, I've only got one more thing to do with this, and then I have to move on from A. I think then I'll do G. And then we'll do nothing but derivations in the hour and a half we have left, which is the part you want. And I will be doing very similar ones to the homework. A lot of you were late for your exam. Okay, now, I normally ask you to do, so we're going to do Clausius inequality for A. This is kind of neat because it's a lot trickier than it seems. Now, hopefully, I'll do Clausius because I kind of feel like maybe we need to do a little bit more reviewing. Let me do Clausius for you again, because I've been repeating everything for you, which is fine. So just to be consistent with what I've been doing. So remember that this is the Clausius inequality. Remember that we were able to figure this out because reversible work is the most negative. Therefore, reversible heat's the most positive. Reversible heat over temperature is entropy. Anyway, that was the natural flow. It led to this. It's really not rocket science. And then that constant volume. Notice again that in this part of the lecture, part of the class, I'm always saying, oh, but what's held constant? And that matters because, experiments, systems are at constant something. And I don't know why my handwriting has decided to fall apart, but okay. There's no experiment, no system, no reactor at constant pressure and volume. Maybe if it's at equilibrium, but then who cares, right? So we have to have something constant. Then we multiply by minus t. And what we're just trying to do there is we're trying to get energy. Because remember, energy is something that's easy to measure. And then we have to invoke something else being held constant. And there we go. Okay, not much to it. And now recall again that this started out with a stipulation on spontaneity, and it ended that way. Nothing changed. The only thing that's actually different now, again, we held things constant. The only thing that's actually slightly funky is multiplying by minus t. That's the only thing that actually kind of perturbs that, but not really. Okay, now I'm going to do A. Now to do A, if some of you, you've already, I see all of you furiously writing. I'm like, but you've already done this because I want to wipe this out. Remember what? No? No? Okay, no. All right. Here, I'll just wipe this out. All right, so let me do A. I'll do A. And now A is a lot different. And you can imagine, I used to put G on the homework, and I didn't because I just didn't have room, so maybe an exam. Okay, now let's do the same thing. Let's do the same thing for A. Now, of course, I'm going to be holding two things constant, but they're not going to be volume and entropy because they're not the natural variables. Okay, A's natural variables, from what I just erased, unfortunately, are volume. So let me start with volume. And now, immediately, you're going to see I'm kind of in a bit of a conundrum. You may have thought that I was going to write change in A, right? Change in heat would just magically turn to change in A, and there's my A, and now I just need to multiply by minus T. Well, A isn't heat. It doesn't work. So, let me multiply by minus T just to get this in the form of energy. Okay, so I'm at where I was before. And so I don't seem to be anywhere near A. And if I hold T constant, so what? There's no change in T in this equation. So this is a bit of a,
If you multiply by minus t, do you have to flip the sign?
Yes, thank you. Yes, of course. 4 is greater than 3, minus 4 is less than 3. Or if I get, if you have that on the exam, I'm kind of leaning towards it, put in numbers, right? It's obvious. Okay, now my problem is I don't see A. I don't see A anywhere. Now let me remind myself, unfortunately, a derivation, I have to stop and do another derivation. Painful when I do that. but necessary. Let's see, and let's do this at constant V. So basically, I'm just going to toss out the, no, sorry. I'm just flattering around like a bit of a fish. Okay. There we go. Okay? All right, now here's the crazy trick. This is how you do this question. This is kind of funky. I really do like this, though, because it's so easy. I mean, it completely changes this, but it's so easy. It's like stupid easy. It's like this is like cheating. Okay. Okay, here's what I wrote before. And notice that I've actually almost got this. All I have to do, see, if I just had this, I got my change in A. But what I can do is just subtract the negative back out. You know, wasn't that clever? You see, I just added 0. Am I still at, no. Not only did I get the sign wrong, I got the units wrong, which I cared so much about. Okay, see that? Anyway, I always thought that was clever. I would have never figured this out on my own. There we go. All right, now notice, of course, we're not done yet. So we have to hold T constant. And often in experimental conditions, T is constant. There we go. A is negative, means something, a reaction is spontaneous. There you go. Constant T, constant D. A is less than 0, means a reaction is spontaneous. Now, let me tell you, I didn't put it on your homework, so that might mean it's going to be on the exam. You would basically do the same trick, but instead of U, you would have H. Right? It's actually relatively trivial. You would be at constant P, and then you have an H in here, and then actually the whole thing flows the same way. So anyway, maybe just make a note of that or try it on your own. It's a very, very simple. If you actually want to keep this, no, you have to do it that way, don't you? Oh, anyway, so I'm going to stop babbling at this point. Oh God, what else is there? I guess I can point out change in G, and I'm not going to do this with. Yeah. Here, let me just now point out what G does, and then let's start doing derivations after that, because God knows I've got a ton of them. So G is the biggest for your Legendre transform, and so let's do dG. And hopefully at this point, this is rather trivial to you at this point. I hope so. It's just wordy. It's just a lot of stuff to write. Okay, minus PdV. And don't worry about trying to memorize if U is minus PdV plus TdS. I don't want you choking at the first step. No, minus. No, plus, minus. I got lost. There we go. And hopefully the camera's reaching all the way across the board. So right, it's not that bad. It's middle school algebra hard. Okay, those are gone. PD, if I lined these up better, it would have been a little bit smoother. But there's my terms. Minus SDT. So I can see that G has T dependence plus BDP, and therefore G has T and P dependence. And it is true again that if you hold T and P constant, here I'll write that down. You should have this. At constant T and P, a delta G, a negative delta G, is spontaneous. Let me just use some shorthand there if you don't mind. It's spontaneous. Again, it's very easy. Just make P constant and put it in H. Don't forget that this is, let me help you out with that as well. Remember that U plus PV is H, so this is H minus TS, which is something you're also probably quite familiar with as well. Okay, so again, we've got two new energy functions. To be blunt, that doubles the number of derivations I can now do, and that's no fooling. So what I've got from now on are nothing but derivations. And again, folks, I want to just strongly point out that what I'll do is always give you a good starting point. Try to make it clear what you're doing. Give you a clear starting point. And as you start writing this out, dg is, I forgot, dg is TD, hey, what's dg dp at constant t? Okay, you write out dg, I'll give that to you. Divide by, what did I say, dp? I already forgot.
Yeah.
Do what? dp, all right, so I divide by dp, and then what will happen is the individual terms will be something kind of obvious. It's like a heat capacity, or maybe I'll tell you that dt dp is something, or maybe use the perfect gas law. It will be trivially obvious. And I'm going to show that to you by doing example after example for the next hour and a half. That's how I'm going to prove that to you. But understand that I might ask you a question I've done in class, I might not. I have 1,300 possibilities. Even if I wanted to do something in class, I might just forget and just slip and write a P instead of a B. Right? So the thing is, you just got to be able to do it. Just got to be able to flow with it. And again, that's like useless advice, I know that. So my answer to that is practice, practice, practice. And that's why you have 8. That's why I'm going to do a whole bunch, and you practice at your, practice on the homeworks. Let's see, now what do I want to do with this? Okay, so let me start showing all the different possibilities, all the different tricks I can throw at you. And, sometimes, maybe if we have, I think I might end slightly early so I could answer specific questions. Or if you felt like, we tried this once, you can maybe just throw letters at me and I'll do X, Y, and Z, and you randomly pick X, Y, and Z, and I'll just see if I can do it. Again, there's 1,300 possibilities. You will probably ask me something I don't know already, just by happenstance. Okay, there's a class of questions. I've been doing this for a long time, and I can kind of see that these derivational questions come in groupings. You probably aren't going to see that even at the end of this class, but I see it. But there are questions that are basically solely dependent on entropy, and so that's kind of like a grouping. So let's see. Let me. What am I going to ask? What am I actually asking? Okay. So the question is, what is ds dt at constant t? Okay. Now, why would someone ask this? Well, driving entropy up in a chemical reaction will make it go, because that's how everything goes. That's the second law. So what I can see from here is if I'm looking at, say, a product, and if I want to know if its entropy goes up or not, and this product is being made in a reactor that's at constant volume, this tells me that, right? So if I want to drive up a product's entropy, which I would if it's a product because I'm trying to make it, do I heat it up or not? Oh, by the way, I'm at a constant volume reactor bed. Now, you'd also have to do that for the reactant and see whether the difference is negative. There's a little bit more to it, but let's not worry about that right now. We actually will do that later. Okay, so this is the question. Now, again, there are, I swear to God, if you pick any, what I'm going to start with is an energy equation. If you pick any energy equation, they'll all lead to the right answer. It's just a matter of steps. Now, what I'm thinking is, I want an energy equation that has a change in S in it already. Not G. G has minus S dt. No G.
Q.
Wait, what?
Q.
Q?
U.
U. Yes. U. Let's do. You know why I like U? Not only does it have ds in it. Is that what? Who said that? I don't know who said that. Anyway, you have a constant v. So that was very clever, by the way. Okay. So now. Now, by the way, I would have told you this. Again, I'm not going to have you start this with G. Not that you wouldn't get the answer, it's just I don't know how long it would take. Probably, 20 steps. You could definitely do it, but that was very clever, by the way, because one of the terms immediately gets wiped out. Okay, so what? Okay, Okay, so this question comes with a hint. The hint is CV is equal to what? Right, this. I hope you remember that, by the way, but I wouldn't presume. Okay, if this was seriously on the test, look at the, I don't know that I'd tell you that because that makes it too easy. It's on the cheat sheet. Of course it's on the cheat sheet. Let's see. Oh, well here, let me just finish it because it's tricky. Okay, there you go. All right, so shockingly easy. This would be the first, in the test this will be one of the early questions because it's just done in a single step. Okay, that's part A. So again, these always come in groupings. This was part A, now here's part B. What's delta S? Okay, what's this? Now that means that you're doing an integration. The way to know that is you've got little Greek d going to big Greek d. Okay, and the way to do this, and this is something I value, is that you know that you can take these partials and split them up. Okay, so that ends up being, again, also very, very simple. Delta S, the limits are S final, S initial, and hopefully you even if you can't do this off your general knowledge of Calc 1, the answer key, the cheat sheet has a calc identity with that anyway. So integral of 1 over x is ln x. So that's in there. Look familiar? Right, now this is what I was telling you, that there are 5 or 6 ways to do the same derivation, every one of these derivations. It's just a matter of number of steps. This guy ends up being kind of easy if you do it using heat, right? Heat over temperature. So, yeah, so there's that. Let's see, let me do 1 or 2 more and then we'll take a break. Let me do 1 more and we'll take a break. And I've just gotten lost in my notes. Okay, hold on. Let's do, what am I doing? Let's do that one. Huh? 42? No, 42 is not the answer to everything. Okay, someone give me a starting point. No, again, I'll give you one, but I'm hoping, I kind of want to get your intuition flowing here. Helmholtz.
G.
Actually, none of them.
Gibbs.
None of them. What I see is a change in S and Ch. So here's the hint. I tell you what, I'll try G in a second, but here's the hint. I got a change in S. Now you know, so that kind of pigeonholes me to H and U. But now I got a P, and P is H's buddy. So that's why now, tell you what, I'll try one of those others in the second hour, just for the heck of it, because as I promised, it ought to give me the answer. It's just a matter of steps. So now again, but it could be 20 steps. That's why I won't have you do that by happenstance. And if you do that, it's because you didn't look at a hint. Now here's another reason to pick this guy. What is this?
CP.
It's what?
CP.
All right, on dHTP at constant t. You've kind of forgotten some stuff from chapter 2. 0. 0, right. Now, in the next hour, I'm going to show you that it depends on whether it's a perfect gas or a real gas. That's because it's on your homework, by the way. But for now, let's say 0. Okay, and now I'm just going to do the algebra. I feel like have I done this right? Yeah, I've done it right. Sorry, just freaked out for a second. Okay, so that's part A. Part B is to integrate. So minus V over T. V is NR over P. I had to think about it for a second. Oh, and I got a minus sign. Okay, so when I integrate both sides, that's the terrible integral. And I'm doing several steps ahead of time. I know a lot of you think I messed up the minus, but I didn't. Did I do that right? Yeah, I did that right. Okay, so anyway. So there's lots of ways to do this stuff. Okay, so let me go back to this. So again, this is formal lecture time, just for 10 minutes, and then I've got a bunch of examples that are absolutely relevant to the homeworks. And they're not, I was careful about, the thing is sometimes I forget what's on the homeworks because I've written so many, and there's so many changes in X with respect to Y and Z, I just literally forget what I have. Okay, anyway. Okay, so let me map back onto this change in U. And again, it may be inconsistent with V's and T's, but just do your best to roll with it. As long as I don't switch in the middle of the derivation, that's where I would legit have screwed up. But regardless. Okay, now, again, definitely I'll have something like this on the exam, and if you really struggle with this, then this is what to do. I mean, I don't, but then again, I've been doing this for years. Okay, df, dx, a constant y. So this is the kind of thing I might ask you, given a change in something, tell me what all the variables are and the conjugates. So once you've identified f and x, and again, as long as I don't switch midstream, we should be okay. And change in y. Okay, again, knowing what f is u, y is v, x is s. Okay, we have this. Okay, now I already wrote this before, but now here's the thing. Here's another tool in our derivational toolkit. You need this on the homework. This is why, unfortunately, I had to spill lecture over into this extra hour. Now, you may recall the Euler Test for exactness. Recall that if a function is exact, if a partial is exact, if is exact. Okay, now again, this is for partials. So if the change in f is exact, if that's an exact partial differential, that means that there is a function f. Remember, don't get that confused. Don't get partials, changes in f, confused with f itself. That's a big mistake. It's a fatal mistake. So if the change in f is exact, then it's true that the order of differentiation doesn't matter. And so I'm doing a double derivative, y and then x, because that's kind of natural, and then I just permute that. Now here's the point. You notice that I've got x's and y's and f's defined. That means that I can turn this into something, right? Let's see. So this is the change. And again, I will be very careful about y's, and I'm not going to switch them. Y is v. Changing u with respect to x is s, constant v, constant s, is a change. Then I permute change in v, change in u, change in s, constant v, constant s.
That's the same thing.
Yeah.
Huh?
Same thing.
Yeah, I'm testing you. You're right, x is s. God, sorry. It's what happens when I roll too fast. What's funny is I get more used to this. I get a lot more tolerant to mistakes. I mean, I'll go to professional talks, I'll see a mistake, and it just doesn't bother me because I'm sure that it was just a fat finger mistake. I rarely see people go to the point of like where they're making a professional presentation where they legit make a mistake, or a mistake other than just they made a fat finger. I'm sure the results that go on from there were fine. Anyway, so. Okay, now I know that this symbology is a little bit like cross-eyed, so what do I do with that? Okay, notice that I've got du ds a constant v defined. I've already told you what du ds a constant v is. What is it? T. Okay, but what do you do with it? The answer is, now I know this is going to sound kind of silly, but seriously this works. It hops on top. dt, dv, at constant S. So the V gets eaten up. Okay, du dv at constant S, what's that? Right, negative P. So just put a minus sign out in front of the whole thing. Okay. This is called a Maxwell relation. Okay, what Maxwell relations are good for is you get in derivations, and half the time, let me tell you what you're going to run into. Du dt at constant V. Now, I know you can't see my words, right? Du dt at constant V, that's heat capacity. Heat capacity, constant volume. It's brainless. You should know that at this point. dt dp at constant V. Perfect gas law. But sometimes you run into ones with entropy in them. Oh, that's not straightforward. That is not straightforward. That is when you want to get rid of the entropy. And that's what Maxwell relations do. They manage to wipe out entropies, ds dt, and instead you get a dv dt. dv dt doesn't scare me because that's perfect gas law. Entropy, with being KLN number of microstates, what the hell do I do with that? What you do is you get rid of it via Maxwell's relation. Now, that seems abstract. I will make it not abstract by doing a bunch of examples. Now, here's another thing. There's 4 of these. Because I've got 4 energy equations as of today. But now there's a trick to this. I'm not going to write all this out again because I think my pen's dying. But let me point out that due to the symmetry of the Euler test, there is an easy trick. The blah at this at constant that. Okay, dt, dv at constant s, and then I permute on the other side. dp, ds at constant v. Oh, but there's a minus sign. Okay, so there you go. Now, some of you may recall that we defined dt dv at constant s last time. I don't quite, what was it? It was minus p over cv. I don't remember that. But recall that we spent some time, I think you guys, that was the lecture I got like really nutso. I think you guys got a little cross-eyed, but recall that I did define this. And if we need it, I'll let you know it or something anyway. Just want to point out that gives me, what's nice about that is that now I can figure out how S changes with P. Anyway, let's not worry about that. That's not related to the examples I want to give. Let me put down the others. Okay, H has always got the same TDS, but it has the pressure dependence switched. Sorry, it removes the volume dependence and has it on pressure. Again, PV is always such a you-know-what because there's the minus sign that keeps modulating. And so that one's a nightmare. Okay, now I can go through this whole analysis, and if I put this on the test, I'm going to want to see you do this. The reason I like Maxwell relation questions on tests is because I want to see that you can follow along with this, that you really understand it. Besides, it's not that hard, but you also can quickly get the answer, and that's what I'm going to do here. Okay, dt dp at constant s. dp at constant s, and that was one of the ones that we did 2 lectures ago. dv ds at constant p. And just write these out yourself to get used to them. It's just like literally flowing, moving your hand right. dv ds at constant p. Okay. dg, let me do a. Minus s dt, that's the one that's all negative. And okay, so this one's all positive, this one's all negative, and that means all the minus signs cancel out. So I'm just going to ignore all the minus. Well, actually, I'll keep them there. I'm going to keep both minus signs. Okay. Change in s, change in v at constant t. Sorry for the overlap. Minus change in p, change in t at constant p. Of course, the minus signs cancel. Okay. So now the minus signs cancel. And let me write G. over here. Okay, now that we're getting into A's and G's, now you can see how it's a little bit more useful. Okay, now remember that entropy is KLN number of microstates. What's the derivative of number of ln microstates with respect to volume? Go to grad school and I'll show you how to do that. It's really quite difficult. We save that for grad school. In this class, you get rid of it. If you run into ds dv at constant t, get rid of it and replace it with dp dt at constant v, which is what? Hopefully you can do it in your head. Perfect gas. nRT over v. nR over v would happen to be p over t. See? See, that's easy, right? No idea a fifth grader could do it. Well, not, okay, high school student could do it. All right. You're a college graduate, so you can do that. So that's the good thing. Now let me do G. Okay, and then I'm going to do homework examples. Minus SD. So G is a hybrid in terms of like pluses and minuses. I always remember that. Okay, minus S dP at constant t. Change it. I just said S. I have to say change in because everything's a change in. Okay, change in V, positive, change in T at constant P. And again, I see that on the right-hand side, dV dt at constant P is again, that's a good one. That's a perfect gas law one. I can definitely do that guy. Okay, let me pray I can get a new pen. Okay, now you need these. The reason I had to spend some time on this is you need these on the homework.